In a quiet stretch of Yangao County, Shanxi Province, engineers recently sealed a train inside a 2-kilometer steel tube, sucked most of the air out of it, and let it go. There was no track friction. There was barely any air resistance. The train didn't run. It flew, just inches above the rail, held up by nothing but magnetic force. This is China's attempt to build the fastest way to travel on land in human history, a system designed to eventually hit 1,000 kilometers per hour, faster than a commercial airliner. And it's not the only transportation project China is racing to finish. While the West debated whether Hyperloop technology was even real, China quietly started building it. Let's start with what this project actually is. It's called T-Flight, and it was developed by the China Aerospace Science and Industry Corporation. CASIC, the same state-owned company that builds China's missiles and rockets. That detail matters because the engineering behind an ultra-high-speed vacuum train and the engineering behind aerospace vehicles overlap more than people expect. Both require managing extreme speed, aerodynamics, and precision control in low-pressure environments. T-Flight is what's sometimes called a vac train or a Maglev Hyperloop. It combines two separate technologies. The first is magnetic levitation, or Maglev, where powerful magnets lift the train off the track entirely, eliminating rolling friction. The second is the vacuum tube itself. Even a levitating train still faces air resistance at extreme speeds, and at 1,000 kilometers per hour, that resistance becomes the single biggest obstacle. So engineers pump most of the air out of the tube, creating a low vacuum environment where the train can move with dramatically less drag. In testing under normal, non-vacuum conditions back in 2024, the T-Flight prototype reached 623 kilometers per hour on a short 2-kilometer track that already broke the previous world record for a superconducting Maglev vehicle. But 623 was only the beginning. The whole point of the vacuum tube is to go well beyond what's possible in open air. In 2026, the project reached a new milestone. Engineers completed a full-scale integrated demonstration test of the system inside the low-vacuum tube in Yangao County. This wasn't just a speed run. It was a test of the entire system working together. Magnetic suspension, braking, curve handling, and the vacuum environment itself all at once. According to officials involved in the project, the train's speed and its suspension height above the track matched the predetermined targets exactly. It handled curves without issue. It came to a stop safely. And critically, the low vacuum environment held steady across the full length of the tube, proving that maintaining that pressure at scale is actually achievable, not just theoretical. Engineers described this as a major step in technical maturity, laying the foundation for the next phase of testing. The ultimate target for the system remains 1,000 kilometers per hour, or about 621 miles per hour. For comparison, a typical commercial airliner cruises at roughly 900 to 1,000 kilometers per hour. If T-Flight hits its target speed, it would move at essentially the same speed as a jet, but on the ground, station to station, with none of the time lost to airport security, boarding, or taxiing. Here's why almost no other country has managed to build this. Maintaining a stable, low-vacuum environment across an entire tube is extraordinarily difficult and expensive. Any leak, any seam that isn't sealed with near-perfect precision, and the vacuum collapses. On T-Flight's test track, the tube surface was reportedly flattened to a tolerance of about 1/3 of a millimeter, a level of manufacturing precision usually reserved for aerospace components, not railway infrastructure. Then there's the cost problem. Professor Andrew McNaughton, a rail engineering expert who has studied these systems, has pointed out that both construction and operating costs for Maglev vacuum systems are substantially higher than conventional high-speed rail. You need specially built tunnels. You need vast amounts of land. You need constant energy input to maintain magnetic propulsion and vacuum pressure. This is also exactly why the American version of this idea, Hyperloop One, backed by Richard Branson and Elon Musk's early Hyperloop concept, collapsed. Hyperloop One raised over $400 million, built a short test track in the Nevada desert, and shut down in 2023 without ever building a commercial route. The concept was sound. The execution at scale never happened. China's approach has been different. Treat it as a long-term state infrastructure project, similar to how it approached high-speed rail 2 decades ago, rather than a venture-backed startup chasing quarterly results. But T-Flight isn't the only piece of this story, because most people will never ride a vacuum train in their lifetime. What will actually change everyday travel for hundreds of millions of people is a more conventional-looking bullet train called the CR450. China's current high-speed rail backbone, the Fuxing series, tops out around 350 kilometers per hour in commercial service. The CR450 is designed to push that to a commercial operating speed of 400 kilometers per hour. During testing, individual CR450 train cars have hit 453 kilometers per hour, and when two CR450 trains passed each other going opposite directions, their combined relative crossing speed was measured at 891 kilometers per hour, faster than the cruising speed of most commercial jets, just measured sideways instead of vertically. CR450 prototype trains rolled off the assembly line in late 2024, and as of 2026, operational assessments and design finalization are underway ahead of entering regular passenger service. Once it does, it will become the fastest commercially operated high-speed train in the world, ahead of Japan's Shinkansen and every European system. And this isn't a one-off showcase project. China's high-speed rail network already covers over 97% of Chinese cities with populations above 500,000. In 2025 alone, the network carried more than 4.588 billion passenger trips. The CR450 isn't a novelty train for tourists. It's the next generation of a system hundreds of millions of ordinary people already use every week. None of this speed matters if the tracks can't physically get where they need to go, and China has also been solving that problem in dramatic fashion. In mid-2026, Chinese engineers completed a major tunneling breakthrough beneath the Yangtze River. A massive tunnel boring machine nicknamed Linghang carved an 3-kilometer stretch beneath the riverbed, the longest distance ever completed by a boring machine of its size, 15 meters wide, in a single continuous run. This is part of the Changtai Yangtze River Tunnel project, which will connect Shanghai's Chongming Island, the country's third largest island, to Taikang in neighboring Jiangsu province. For the first time, Chongming Island will have direct high-speed rail access. The tunnel is scheduled for completion by the end of 2026, and it's specifically engineered to support the next generation of ultra-fast trains, including systems built around the CR450 standard. Boring an 11-kilometer tunnel under a major river isn't just a civil engineering flex. It solves the actual bottleneck that limits how fast and how far high-speed rail networks can expand. Geography. Rivers, mountains, and dense urban centers have always been the hard limits on rail infrastructure. China is now treating those limits as engineering problems to be solved, not permanent obstacles. It's worth remembering that China isn't starting from zero on any of this. Back in 2021, China's state-owned rail manufacturer CRRC unveiled a 600-kilometer-per-hour high-speed Maglev train in Qingdao, a system specifically designed to fill the gap between conventional high-speed rail at around 350 kilometers per hour and air travel at 900 to 1,000 kilometers per hour. That train doesn't need a vacuum tube. It floats on magnetic levitation through normal open air, and it's already been demonstrated publicly, with route planning studies underway for potential commercial lines. So by 2026, China effectively has 3 tiers of next-generation transportation developing in parallel. Conventional high-speed rail is pushing toward 400 kilometers per hour with the CR450. Open-air maglev already runs at 600 kilometers per hour, and vacuum tube maglev, T-Flight, is targeting 1,000 kilometers per hour. Most countries are still trying to build a single high-speed rail line. China is simultaneously developing the entire spectrum of ground transportation speed, from 350 all the way up to airliner velocity. This isn't just about bragging rights over top speed numbers. There's a real economic logic here. Short-haul flights are inefficient, expensive to operate, and among the most carbon-intensive forms of travel per mile. If a train can realistically replace a 1 to 2 hour flight between major cities, it changes airport congestion, fuel demand, and regional economic connectivity all at once. Chinese planners have been explicit that a faster, denser rail network is intended to bind together industrial and population centers that are currently separated by hours of travel time, effectively shrinking the economic map of the country. There's also a manufacturing dimension. Every kilometer of maglev track, every boring machine, every train set built for these systems represents a domestic industrial base that China is developing years, sometimes decades, ahead of most competitors. When export markets eventually open up, and China has already discussed maglev and high-speed rail exports to Southeast Asia, the Middle East, and parts of Africa, China won't just be selling trains. It'll be selling an entire vertically integrated transportation industry that almost no other country can currently replicate at this speed or this cost. It's worth putting China's position in global context. Japan's SC Maglev L0 set the previous crewed maglev speed record back in 2015 at just over 600 kilometers per hour, and that record still stands as the official benchmark for a train carrying passengers. As of 2026, no Hyperloop or vacuum tube train anywhere in the world carries paying passengers. Not in China, not anywhere. America actually tried to build this first. Hyperloop 1, backed at various points by Richard Branson and inspired by Elon Musk's original Hyperloop concept, raised more than $400 million in venture funding, built a short test track in the Nevada desert, and shut down completely in 2023 without ever completing a commercial route. The concept was sound. The execution, at scale, never happened. China's approach has been fundamentally different, treating this as a decades-long state infrastructure project, the same model that built its existing 0-kilometer high-speed rail network, rather than a venture-backed startup chasing quarterly results and exit valuations. That patience is exactly why China is currently the only country in the world running a full-scale vacuum maglev test line. To be clear, none of these systems are in commercial passenger service yet. T-Flight, the CR450, and the Yangtze River Tunnel are all still in testing or under construction. Building and maintaining a vacuum tube at scale remains enormously expensive, and experts like Professor Andrew McNaughton remain genuinely divided on long-term commercial viability, particularly in regions with sparse population density, where the economics simply may not work. The United States and Europe also still lead in areas China has far less experience in, especially long-haul aviation and aerospace manufacturing at commercial scale. This isn't a story of America falling behind across the board, but in one specific category, ground-based, ultra-high-speed transportation, China is years ahead of any other country currently testing at this scale. Nobody else has a full-scale vacuum tube test line running. Nobody else has a 400-kilometer-per-hour bullet train entering final assessment. Nobody else is boring 11-kilometer tunnels under major rivers to support next-generation rail. The trajectory is clear, even if the destination isn't guaranteed yet. Looking ahead, the next phase of T-Flight testing is expected to push closer to the full 1,000-kilometer-per-hour target, likely on a longer test track than the current 2-kilometer line. CR450 trains are expected to enter regular passenger service in the coming years, gradually replacing parts of the existing Fuxing fleet on China's busiest corridors. The Changtai Yangtze River Tunnel is scheduled for completion by the end of 2026, opening new high-speed rail access to Chongming Island for the first time in its history. If even one of these systems reaches full commercial service before anywhere else in the world, it resets the global benchmark for what ground transportation can do. China has also begun discussing exports of its high-speed rail and Maglev technology to Southeast Asia, the Middle East, and parts of Africa, meaning this isn't just a domestic infrastructure story anymore. In the race to build what comes after the airplane, China currently has the only trains actually inside the tube. If this video gave you a clearer picture of where transportation is actually heading, hit subscribe to follow more research-driven analysis like this. The next video looks at another race China is quietly winning. Thanks for watching.